You should see. There we go. And then we will share this afterwards on our website as well as an email. So we'll go ahead and get started. Today we have Dan Hahne presenting on low pressure VAV systems. So I'm not going to steal too much of his thunder on his introduction. So I will just hand it right over to you, Dan.
Kelly, thank you very much. And thank all of you for joining us today on another session of Webinar Wednesdays as we address solutions that are advocated by ASHRAE, the CDC, the EPA for creating healthier buildings with reduced risk of infection. So I'm going to go ahead and try to share my screen. It's always somewhat of an adventure. Let's hope that we succeed. And hopefully you have a full screen.
You're good.
Thank you, Kelly. Let's begin. First of all, an introduction. I've done this every session, but we've had an increase in the number of people attending these sessions today. So just a brief introduction. Again, my name is Dan Hahne. I've been in the industry for over 35 years. I began in 1985 working as an estimator for a manufacturer's rep firm called Norman S. Wright. I joined a company in 2000 as an outside salesman called Air Specialty Products and worked with ASP, sorry for the typo, until 2016. In 2008, however, I had the opportunity to become involved as a sales engineer for Air Specialty Products. And when I did so, I must confess I had something of a mission. I really wanted to advance high-performance HVAC systems. I thought it was where the market was trending. ASHRAE supported that with standard 90.1 documents, as well as various pressures globally with regard to the environment. So we began to advance high-performance HVAC systems in our market. And in 2016, Varitec Solutions reached out to me and asked me to join them as their corporate educator. And that's what I've done. And with the development of the unfortunate development of the pandemic, I thought it would be a good opportunity to educate myself on what are the causes of infection in the environment, what environmental influences increase the risk of infection, and what HVAC system solutions offer the best way to reduce the risk. In doing so, I went immediately to ASHRAE to do so, as we will review quickly. If any of you who do not know who Varitec Solutions is, we are an HVAC system solution provider. We've been in the industry for over 45 years and have a market presence throughout the southwestern United States from San Diego through to Lubbock, Texas. And we can provide HVAC equipment and now integrated HVAC systems designed for any type of building application, healthcare facilities, education, government, institutional buildings, and even just small business centers. So we can actually look at a building, and depending on the owner's intent, available budget, etc., we can evaluate what type of system approach might most effectively meet their needs, as well as save them as much money as possible throughout the operating cost of that system. In light of the developing nature of our of the politics of global warming, the movements to reduce the amount of energy consumed by buildings, since buildings consume 40% of the overall energy consumed in this country, Varitec has adopted a platform to always keep in mind to shaping the future and where HVAC is going. And this is the realm that I'm pretty much involved in. And we built in 2019, toward the end of 2019, 2020, the Varitec Technical Institute with this mission statement: to provide an educational platform for continued learning in the HVAC industry with a focus on high-performance buildings and innovative technologies for a better built environment. Well, in saying that, hopefully this day advances our objective in being that resource to give you information to consider when you're faced with your next retrofit building design or new construction. For today's event, however, I have to acknowledge the resources I've drawn from Acutherm, the Center for Disease Control, ASHRAE, the handbooks, the standards, Daikin, and Taylor Engineers for their information on low pressure systems. So today's agenda, we're going to cover the following. We're going to give you an update on COVID-19 transmission. We're going to do a quick review of Webinar Wednesday, what we have done, why we have done what we have done, and where we are going and why. We're going to look at ASHRAE Epidemic Task Force language, the very starting point that we began this series from. And we're going to look at not only the ASHRAE Epidemic Task Force language for reducing the risk of infection, we're going to look at language from the CDC and the EPA and what is meant by infection control bundles. Then we're going to look at the topic of this discussion because it's so important that when you look at an HVAC system, you look at it in context. It isn't just something that is arbitrarily sitting out there that we can cut and paste and adopt to a building. It's very important, I believe, that we put it into context. So we're going to address how low pressure HVAC systems can utilize one of the recommendations by ASHRAE for enhancing dilution in a space to reduce the risk of areas of concentration of active pathogens. We're going to go into what a medium pressure VAV system is so that we can make an informed comparison. Then we're going to address low pressure VAV systems and then energy efficiency and how low pressure VAV is conducive to the growing trend of electrification and decarbonization. So first of all, an update on COVID-19 transmission. On October 1st, the New York Times published an article, "Is the coronavirus getting better at airborne transmission?" The article goes on to state that newer variants of the coronavirus like Alpha and Delta are highly contagious, infecting far more people than the original virus. People infected with Alpha exhaled about 43 times more viral load into tiny aerosols than those infected with older variants. Consequently, the Alpha B117 variant that was introduced into the UK in 2021 is now responsible for 95% of the new SARS-CoV-2 infections in England. So that bears out that this virus, we hope, will play out and come to an end, but there are still mutations occurring out there that could challenge us in the future in ways we don't really fully know yet. Another thing I want to cover is what is the current trend of infection in the United States. In previous presentations, we reviewed how certain conditions seem to be conducive to what we know as cold and flu season. Cooler climate, people spending more time indoors, part load conditions within a building for air conditioning needs. It's our driest time of the year. Dry environments are more conducive to infection spread, as we covered in our humidification presentation. And of course, flu and cold season begins. It wouldn't surprise me to see that we will see, as the map suggests, a spike in COVID-19. Let us hope it doesn't reach levels that we experienced in this summer or certainly experienced in the spring. So hopefully with the vaccinations, we will see that we will not reach those levels. So Webinar Wednesday. Why did we build the webinar series? Well, again, we felt it was important that we get out into the industry, good information grounded in the science and engineering principles ASHRAE has brought into this market, and we endeavored to do so. So the part one grouping of sessions involved resources and technologies. We started with the very publication of the ASHRAE website, the Epidemic Task Force. And we did a review of how to navigate the task force website because it is a little bit of a deep dive rabbit warren to extract the information you need to make the decisions that you may need to make. We then covered the physics of pathogen migration. We had the good fortune to have Hoy Bohannon, distinguished lecturer of ASHRAE, present on Standard 62.1 and the importance of ventilation. We did humidification. We did UVC light technology that is openly advocated by ASHRAE as a pathogen mitigation solution. We had the good fortune to have David Shirk, I believe he's Director of Development with GPS, explain to us why needlepoint bipolar ionization and ion technology can reduce the risk of infection. So we looked at individual layers of solutions that we can apply and went into the physics of them, how they operate and perform, to give us a better understanding of their applications. Part 2 of this webinar series is looking at what ASHRAE advocates as a bundled solution to maximize the reduction of infection in buildings. There's no one silver bullet. There's no one solution that will kill pathogens within an environment. There's only percentages of effectiveness with applied technologies. Consequently, if you provide bundles of technologies into an HVAC design, you are very likely to create a healthier environment with a reduced risk of infection. So we had, again, the good fortune of having ASHRAE Fellow, distinguished lecturer, and a most impressive individual, Chris Mathis, speak to us on why buildings matter and why Standard 90.1 is aggressively moving in the direction it is for enhanced energy efficiency. We have this session on low pressure control, or low pressure VAV systems. The next session in December, we're going to look at pathogen mitigation. How do we bring these technologies and resources together with an integrated system design, starting with just package DX rooftop units, and how do we use these resources to create healthier environments? And then we're going to look at 100% outside air systems. We're going to offer part 1 and part 2, and again, bundled, layered solutions as applied to 100% outside air solutions. So that's the direction the webinar series is going. And we hope you continue to find the information relevant. To begin today, let's start with where we started back in February, ASHRAE's Epidemic Task Force. We're going to start with some terminology drawn from the position document on infectious aerosols that we've already covered many times, but we're going to cover it again. HVAC systems can have a major effect on the transmission from the primary host of a building to secondary hosts. It then goes on to say in the COVID-19 statements that ventilation and filtration can reduce the airborne concentration of SARS-CoV-2. Remember in our discussion that though ASHRAE had been advocating aerosolized transmission since April of 2020, the CDC and the World Health Organization did not adopt that language until November of last year. So ASHRAE was 6 months ahead of the CDC and the World Health Organization in that recognition and advocated solutions at that time. So very grateful for ASHRAE's proactive nature in getting good information into the market. The position document then goes on to address various approaches for various facility types. And it leans on ASHRAE Standard 170. And in that, it states that the role of indoor air management has become critical to successful prevention efforts. It then goes on to say that in view of a broad understanding of flexible pathogen transmission modes, healthcare facilities now use multiple modalities simultaneously. And that is interesting how the Epidemic Task Force is leaning on Standard 170 as direction for adopting a multiple modality or bundled approach for HVAC designs to create healthier buildings. The position document in its ventilation and air cleaning strategies goes on to suggest, which brings us into today's discussion, various HVAC strategies that have the potential to reduce the risk of infection. And of course, one of them is air distribution patterns, and we'll be covering that in greater detail shortly. The core recommendations for reducing airborne infections goes on to state in paragraph 3 under air distribution that when directional airflow is not specifically required or not recommended as the result of a risk assessment, promote mixing of space air without causing strong air currents that increase direct transmission from person to person. I would have to think that that leans on standard 55's direction to provide air at roughly 50 feet per minute at the occupied zone or 5 feet off the floor would meet that requirement. So just be aware of that. So ASHRAE is promoting mixing of space air to reduce area concentrations of contaminant and active pathogens. The ASHRAE positions document then goes on to say that an integrated design process should be applied to provide the appropriate infection control bundle. So I provided here the various resources and technologies webinar series that we've done to show how that we can apply various technologies to create a bundled approach or a layered approach in the HVAC design to reduce the risk of infection. Let's look at what the CDC has to say with regard to mitigating the risk of infection. The CDC recommends in their Ventilation in Buildings webpage a layered approach to reduce exposures to SARS-CoV-2. One of those approaches involves the improvement of building ventilation. In fact, if you remember when we did the presentation on the physics of pathogen migration, we brought up the example of the Guangzhou restaurant in China that really became the benchmark for demonstrating how improperly ventilated spaces is conducive to super spreader events. The CDC goes on to say protective ventilation practices and interventions can reduce the airborne concentrations and reduce the overall viral dose to occupants. So this is public language out there now in the built environment. Information is getting out there, recommendations are getting distributed from our leading federal healthcare authorities. The Environmental Protection Agency goes on to state that an important approach to lowering concentrations of indoor air pollutants or contaminants, including any viruses that may be in the air, is to increase ventilation, which the EPA says is the amount of outdoor air coming indoors. So we have a lot of ballast to demonstrate why a presentation today on dilution, ventilation, and air patterns is relevant in evaluating how we can create a healthier environment. So let's move into this topic of discussion: dilution, ventilation, and air patterns. First of all, let's revisit the EPA's definition of ventilation as the amount of outdoor air coming indoors. And you know, I used to associate ventilation with outdoor air as well, and you can. However, let's go back to ASHRAE 62.1 that defines the amount of ventilation for a building. The definition of ventilation for ASHRAE 62.1 is the process of supplying air to or removing air from a space for the purpose of controlling air contaminant levels, humidity, or temperature within the space. The ASHRAE Handbook Fundamentals 2021 states that ventilation air may be composed of mechanical or natural ventilation, infiltration, treated recirculated air, transfer air, or an appropriate combination. So, ventilation and air exchange rate. Let's be clear. If you thought in the past that ventilation air is the outside air, you would be correct for a 100% outside air system, because that's the only air provided to a building. However, Ventilation air is the volume of air supplied to a space comprised of outside air and any other source defined by ASHRAE's 2021 Fundamentals Handbook, as we just mentioned above. In 100% outside air systems, such as chilled beams, or even 100% outside air variable refrigerant system, ventilation air would be 100% outside air. The ASHRAE Handbook 2021 goes on to state that air change rate compares airflow to the volume of a space. In order to create appropriate ventilation, we have to be able to assess how much air is delivered to that space and exhausted out of that space within a given period of time to make sure we're flushing out the space adequately. Chris So, Daikin's application engineer, goes on to state that air exchange rate is the air change rate that compares the airflow to the space's volume and is expressed by the equation ACH equals Q over V. Chris goes on to state that the air exchange rate used to describe the amount of outside air or ventilation air entering a building or occupied zone. But the question is, since the pandemic, what is the appropriate ventilation rate in a space to reduce the risk of infection? Unfortunately, we don't have any, according to Chris's publication, we don't have any recommendation on the ideal ACH. We don't know at this time. ASHRAE is saying, with regard to building spaces, a minimum requirement is to make sure that spaces within a building are receiving the minimum outdoor air prescribed by standard 62.1, and that will vary depending on room usage, occupant activity, and applications. So just be aware of that. But again, that is a bare minimum. So why? Well, the reason is, and one of the challenges is that we just talked about with the coronavirus alpha variant. What virus are we dealing with? Because the type of virus impacts its rate of production within the infected person. Which variant are we dealing with? Regardless, Chris So goes on to say that most experts suggest at least 3 air changes per hour in a space to provide adequate or modest air change rates to create a healthier environment. Ideally, he goes on to say they're looking at 4 to 6 air changes per hour, which does make sense for this reason. What do we design our hospital rooms to? Well, ASHRAE Standard 170 designs our hospital operating rooms to 20 air changes per hour. We have isolation rooms, airborne infection and protected environments designed to 12 air changes per hour, whereas we have a conventional patient room designed at 6 air changes per hour. So air change rates do promote healthier, or the amount of air change rate can impact the IAQ of a space and the reduced risk of infection. So that covers the section on ventilation. What about air patterns, which brings us fully into the discussion of low pressure VAV? Air patterns in a space are designed to provide a fully mixed environment at peak load. At peak load summer design condition, when we're in maximum cooling, 55-degree air is injected into the space at high velocity. 150 feet per minute out of a diffuser is what we normally see at peak flow. Room air is entrained into that supply air jet out of a diffuser, allowing that 55-degree air to change quickly, rise in temperature, and to provide thorough mixing of the environment, resulting in a uniformity of temperature throughout the cubic volume of space. This is achieved by injecting air at high velocity, as I discussed, I believe, in the July session on thermal stratification. We need that high velocity so air along the surface it travels achieves what is called coanda. Due to the negative pressure effect of high velocity air moving along a static surface, the air will hug the ceiling and induce room air into that supply air jet, it creates mixing. So you need high velocity air to do that. High velocity means higher pressure differential, which means greater mixing. Lower velocity means lower pressure differential and less mixing of the space air. Well, when do we find peak supply air out of our ceiling diffusers? That is usually at our peak summer design condition. By the way, what percentage of the year, what percentage of annualized hours are we at peak summer design? Now, it varies per zone, per region, of course. But I think here in Arizona, Phoenix, Arizona, Maricopa County, we're at 2 to 3% of peak load, which would be 115. Some engineers are now designing to 120, probably a good idea. So at peak flow, we have maximum air supplied to a building. Air is discharged from the diffusers at peak velocity. We have thorough and complete mixing of a space. Consequently, if you have that churn, that ventilation, that air pattern of high velocity in the space, you mix up particles in the space. Conceptually, we argue that maybe it doesn't completely happen in our July presentation on thermally stratified environments, but conceptually and for the most part, you do get a dispersion of contaminant and particles in the space, which means that anybody occupying any zone will be breathing in the minimum amount of concentration at any point within the space. At least that is the assigned objective. However, what do we do when we're in part load conditions and we're in a variable air volume system? When we go to part load, we see a reduction in room load. So less air is supplied to the space at 55 degrees. VAV boxes modulate to a minimum position in order to control the room to the thermostat set point. Well, lower volume of supply air equals lower diffuser discharge velocity. Negative buoyancy takes over. Cool air at low velocity has a tendency to dump into the space. And the question is asked, do we have mixing? And I would say mixing is compromised. So is there a solution, especially in this day of pandemic, to resolve the part load mixing dilemma? ASHRAE says yes. You can find it in ASHRAE Standard 170. How does 170 deal with it? Well, if you look at an airborne isolation infection room that requires 12 air changes per hour, we have to provide the air at 55 degrees for dehumidification at the air handler. We use reheat. That way we can maintain the flow of air to the space, create the churn in the environment that is conducive to a mixed air condition. The problem is that reheat is one of the biggest energy hogs in hospital applications. It is very expensive to cool air all the way down to 55 and then heat it back up again. So it's very inefficient and it is very expensive to operate, though it is a solution. So let's first of all, before we go to low pressure, evaluate a medium pressure VAV system. What is the design intent and purpose of a variable air volume system? Well, ASHRAE Handbook 2016 in the HVAC systems and equipment defines VAV terminals as that solution that controls the space temperature by varying the volume of cool supply air from the air handling unit to match the actual cooling load. So you only get the amount of 55-degree air into the space to maintain space set point temperature. The supply air temperature in these systems is held relatively constant. These systems, medium pressure VAV systems, are usually designed at an inlet static pressure of 0.4 to 0.5 inches water column. These VAV boxes need 0.4 inches of inlet static in order to accurately measure the airflow available at the box. And you have to be able to measure in order to assign the appropriate flow to the room to meet space set point temperature. At 0.04 inches water column, you'll see a main duct static pressure, certainly toward the inlet of the air or the outlet of the air handler, of roughly 1¼ inches of total pressure, maybe up to 1½ inches of pressure. So let's look at the objective as stated in the ASHRAE handbook as to a VAV system. In order to provide some control of flow throughout a building, we actually modulate airflow to a number of rooms to the control set point of an assigned given room. As displayed here is design set point for the thermostat in one office. But what is the challenge of this design with regard to thermal comfort? Well, people start coming into the building, the load profiles per zone begin to vary, and we start seeing fluctuations in space temperature. So as offices are fully occupied, VAV boxes maintain set point for the zone with the thermostat only, and other rooms get the amount of air assigned by the thermostat in the control room. Consequently, if people move around the space, you run the risk of overcooling or undercooling other zones other than the room with the thermostat. So consequently, thermal comfort issues can result. So what are low pressure VAV systems and how can they address the situation or the condition of dilution recommended by ASHRAE's Epidemic Task Force and provide a solution for enhanced thermal comfort? First of all, Steve Taylor of Taylor Engineers has advocated for years, and impressively so, that there are single inlet VAV box design solutions that can be controlled down to low pressures of the 0.3 inches. So there is a low pressure design strategy out there that has obviously been very effective that goes below 0.4. I've not read that it goes below 0.3, but that could be my own ignorance. So anyway, be aware there is a single inlet VAV box low pressure design solution. However, what if we rethink the VAV box solution? What if we put variable volume control in the diffusers? What do we see as an effect? Well, what we hope to demonstrate is you can maximize zone air distribution not only at peak load, but throughout part load conditions. You can optimize thermal comfort, and you have an added advantage of improved HVAC system efficiency, as well as other opportunities as well, such as simple control solutions. So what is a VAV ceiling mounted diffuser? First of all, it is not a new technology. It's been around effectively for 40 years. And I understand from our manufacturer that we represent that they have diffusers that have been operating for 20 years in New York high-rises. The conventional old-style design is a thermally actuated design. It requires no power or wires. There are thermal actuators embedded within the diffuser itself. Hopefully you can see my cursor, that will actually react to ambient temperature around the valves. And the supply air is injected into the diffuser through the inlet and is ejected into the space through nozzles. A negative pressure zone is created in the diffuser on one side, drawing room air across the diffuser that these thermal actuators react to with a highly reactive wax element that expands and contracts at very low temperature differentials. And these elements will adjust the amount of free area available at the diffusers to maintain discharge velocity. There are also DDC VAV diffuser solutions that could be offer a fully electronic control solution at each device, as well as provide backnet networking, so each diffuser can be read by the front end and evaluated for performance. So as discussed, once the room air is measured, the vanes in the diffuser open and close to provide or relieve into the space that amount of air necessary at the appropriate high velocity discharge necessary to maintain room temperature set point. So it is a thermally actuated variable flow diffuser that always maintains discharge velocity, even in part load conditions, meaning that coenda is maintained, throw of the diffuser, air throw is appropriate. We have maximum induction of room air into the supply air jet that is conducive for thorough mixing. VAV ceiling diffuser systems can operate easily at 50% of turn down, and because of the geometry of the internal device and its ability to respond to a temperature very accurately, it can maintain discharge velocity and room air induction into the supply air jet. Consequently, under CFD analysis, computational fluid dynamic analysis, it can be demonstrated that a room maintains a mixed air thermal profile, not only at 100% of load, but also at 25% of load. And since ASHRAE states very clearly that room contaminants and particles follow the direction of air movement in the space, we have every reason to believe that contaminants, particles, and germicides will follow the same flow patterns in that space. So from a thermal comfort standpoint, how can a low pressure VAV work as a good solution? Let's go back to the conventional VAV box. One thermostat in a room, usually it is the senior management's room, and the other rooms get the temperature that they get in order to meet the temperature requirements or temperature set point of the control room. What if we took that VAV technology and dropped it into each diffuser so that only the amount of air is necessary per each room in order for it to maintain room set point temperature? Consequently, as occupants start moving into the spaces throughout the day, depending on what that occupant assigns as being the diffuser set point temperature, we can satisfy the thermal comfort needs of any of the occupants in any of the zones. It's really a very simple, eloquent solution that has been around for 40 years. Consequently, as you have shifts of people to various various zones, we'll find that each of those diffusers will maintain the room at its design value without running the risk of overcooling or undercooling a space in adjacent zones. So it is a very good solution. A VAV diffuser is a very good solution for maximize mixing in the space by always supplying high velocity air at maximum peak load and part load conditions, as well as meeting the thermal comfort requirements of its occupants. So what does that mean with regard to energy efficiency? What can low pressure VAV offer to reduce the amount of energy consumed by a building? Well, first of all, as we all know, high performance HVAC design is here. We at Varitec had the good fortune to have the Daikin National Sales Meeting here in Scottsdale this year. And one of the main platforms that it was bringing in to their rep network awareness was the importance of electrification and decarbonization. We're seeing a direction and movement of many institutional facilities seriously considering what they can do to reduce the carbon footprint of their building, not only through the construction of the facility itself, but also throughout the operating life of the building. Going with electrification, we have learned that a system, an electrical grid that goes down, can respond more quickly than other infrastructure requirements, such as natural gas, certainly in areas of high floodplain regions that we're seeing in various areas of the Southwest along the East Coast seaboards. So we're seeing a movement towards electrification and decarbonization. To give you an example, the UC Berkeley Goldman School of Public Policy adopted electrification as a design requirement in its HVAC operation. And it was able to achieve that using rooftop heat pumps, smart VAV ceiling diffusers, electric radiant heat, and other solutions as well. So it is conditioned and maintained in operation purely by electricity without the use of natural gas. Well, in promoting high-performance HVAC systems, one thing that I've become aware of over the years is that to make sure a system is efficient, you want to minimize on-off cycling, and you really want to most effectively ride the building load. You want to make sure that your HVAC system is only consuming that amount of energy needed to meet the building load and each individual zone load at any given time of day, at any given time of year. That is what is necessary for high-performance HVAC. Now, as Chris Mathis advocated most effectively in his Why Buildings Matter, he demonstrated that one of the greatest items that we can address to make high-performance buildings is to reduce the amount of building leakage. How much conditioned air are we pumping from the building into the outdoor environment due to leakage in the skin, due to piping holes or whatever in a building? So please be aware there are other considerations as well than adopting an HVAC solution that need to be addressed, if not equally, perhaps even more so according to Chris's position. So the more we can increase individual zone control, so we're only supplying that amount of conditioned air necessary to meet not only the north quad of a building, but each individual office or conference room or open office area that we need. We only consume that amount of energy to meet that space condition. We will begin to create high-performance HVAC systems. Well, let's look at a medium pressure VAV system. What are some of the design requirements that we normally see? In order to maintain 0.4 of an inch of inlet static pressure at the VAV box that is furthest from the air handler, we need to create a duct main static pressure of roughly about 1.25 inches. Air travels down the duct at 2,000 feet per minute. And in this example, given to me by Acutherm, they demonstrated that under these conditions, fan energy would be somewhere in the realm of 730 watts. So how does that compare to a low pressure system duct design? If we remember going back when looking at the VAV diffuser and how that diffuser operates, for the diffuser to operate properly, it needs a minimum of 0.05 inches of inlet static pressure, not 0.4 inches, 0.05 inches. To optimize the low pressure advantage of this design solution, reducing the airflow through the duct is necessary, roughly to about 1,000 feet per minute versus a medium pressure VAV solution at 2,000 feet per minute. The duct size will need to increase. If we look here at this proposed design, there's a duct size of 314 inches by 96 inches. For the medium pressure solution, duct design was 216 inches by 66 inches. So the ducts will get larger to reduce the velocity to make sure that the VAV diffusers and static pressure controllers receive the assigned inlet pressure for the system to operate. But look at what advantage such a design can offer. Reduce duct static pressures by up to 1 inch. Fan savings conceptually now is considerable. Under these conditions, fan operation consumes roughly 487 watts. So if we do a comparison between a VAV box system designed to 0.4 inches of inlet pressure versus a diffuser at 0.05 inches of pressure, we take into account the larger duct size, which does add cost. If we look at the resulting static pressure at the fan being radically reduced to 0.25 inches from 1.25 inches, there's substantial energy savings to be had for that. And that is a very interesting concept, because if we look at the ASHRAE Epidemic Task Force guidelines for reducing the risk of infection, ASHRAE quite rightly recommends enhanced filtration, MERV 13 filtration minimum, preferably 14. That adds static pressure to a system. That requires an increase of energy. ASHRAE also recommends increasing the amount of outside air. Conditioning outside air adds a significant energy burden to a building, higher costs of operation. So the purpose of this presentation is to demonstrate maybe we can create healthier environments with superior IAQ and reduce the risk of infection without paying an operational premium if we balance the added costs associated with these systems. For example, if we can pick up 1 inch of static pressure using low pressure VAV, we could add the MERV 13 filtration without paying the energy penalty. So these are some of the considerations to keep in mind, that maybe we just need to think through some of these programs so that we can come up with a good design where owners do not necessarily need to pay a premium every year for the operational costs of their buildings. Please be aware that low pressure VAV ceiling diffuser solutions come in 2 types of control strategies. There's the mechanical control design, where each diffuser vane position is controlled by thermal actuators. No wiring or DDC control is necessary. Each diffuser responds to its own ambient condition of room air induced across the thermal actuators for them to react to adjust the diffuser vane position to supply only the appropriate amount of air at the appropriate velocity to maintain room temperature as well as thorough mixing in the space. Main duct pressure can be maintained by duct static pressure sensors in large systems where you have a considerable number of VAV diffusers served by a branch line. We would put a duct static pressure controller with a duct static pressure sensor that can make that branch duct operate at whatever assigned static pressure we give it. I like to look at 0.15 inches of static as a good medium for those pressure zones. So we can do all of this mechanically through static pressure. So consequently, where you can save money in a mechanical design is in the control side. Really what you need to do is monitor what's happening at the air handler with the amount of fan energy consumed, and the rest of the system can operate rather elegantly and simply under static pressure control. So pretty interesting concept. More modern and flexible designs involve DDC control strategies using 24-volt power. 24-volt power is run to each diffuser and/or static pressure controller in areas serving large banks of VAV diffusers with digital controls. We have electric actuator that opens and closes the discharge vanes to provide the necessary flow rate and high velocity discharge to secure the advantages of dilution for a mixed air system. Duct static pressure controllers are available in these zones, and every diffuser now can talk to a front end where the front air can see the performance of the diffuser, and all of its back net control points become available. So you can use this design concept mechanically in very simple installations, such as a package DX unit serving multiple zones. If your goal is to enhance mixing in the spaces to create a more risk-free environment, you can achieve that. And you can achieve energy efficiency depending on the type of air handler you're using. If it's a constant volume air handler, the only energy advantage you can have is if you have a high efficiency package DX unit. Its fan flow will be at constant volume, and the energy performance is based on the amount of energy consumed to meet the overall building load. However, the diffusers will operate mechanically. Vanes of the diffusers open and close individually per zone. So whether or not you're at full or part load, you're getting thorough mixing in the space, and any extra air is either returned through a non-ducted return plenum back to the air handler, or an ducted plenum of bypass valve is used to dump supply air into the return air path to maintain building pressure in the supply air main. We can use this concept for larger zone applications of multiple VAV diffusers, all for one static pressure controller, all mechanically operated without any DDC control or power wiring necessary. And then we would actually monitor and control the air handler to make sure it was providing the right amount of conditioned air to the space or to the duct system to maintain the static pressure relationships. So to give you an idea of a high performance building solution, we're going to look at a DDC VAV system and how this might look. Here we have an electronically operated system that is conducive to high performance building design. With a DDC solution, we provide full digital control of airflow through each diffuser, full monitoring and control through a BMS, and then if we use one of the new smart air handling units available, DX air handling units provided by Aon, Daikin, or other manufacturers as well, we can now provide an air handler that will use ECM motor technology to respond to provide only the amount of air necessary to maintain the proper flow in the main duct system to maintain pressure relationships. We can vary compressors so that we only have that amount of refrigerant flow necessary to meet the thermal load of the space. So we can create a system that is in conformance to the design intent of high performance building by riding that building load most effectively, not only by supplying only that amount of air necessary at a space to maintain room set point temperature, the air handler itself is responding and consuming only that amount of energy necessary to provide the control of airflow and air conditions necessary to meet that building load. So that is something to consider if you're evaluating low pressure VAV systems, is using considering using smarter air handler technology that is more responsive to specific load to enhance system performance and efficiency. So with today's webinar, we have covered a number of topics. I hope you found them valuable. We covered why low pressure VAC systems make sense, why low pressure VAV sealing air distribution systems can provide the space air dilution during low load conditions to create healthier environments and reduce the risk of infection. We can enhance thermal comfort while doing that through individual zone control. And we have the opportunity to increase energy efficiency through low pressure designs. And if we apply the right air handler, we can even add another layer of efficiency and performance by looking at some of the smart technology available in the market today. And we could also consider using HVAC design solution for the industry moving toward electrification and decarbonization. Any questions?
So right now we don't have any questions in the chat, but if anybody does have any questions, you can come off mute or type them in the chat. All right, so I don't think we have any questions at this point, Dan.
All right, Kelly, very good.
All right, if anybody does come up with any questions afterwards, feel free to email either myself or Dan and we'll help you out.
Well, thank all of you for your time and joining us today.